Welcome. Today we're diving into the fascinating world of convolutional neural networks or CNNs and how they revolutionize image recognition. Whether you're new to artificial intelligence or just curious about how computers can see and interpret images, this video will break down the essentials in a clear and approachable way. We'll start by understanding what CNNs are, why they're so effective for image tasks, and how they mimic the way our own brains process visual information. So let's embark on this journey to unravel the magic behind image recognition technology. Convolutional neural network, or CNN, is a specialized type of artificial neural network designed to process data with a grid-like topology such as images. Unlike traditional neural networks, CNNs are particularly good at picking out patterns and features in visual data. They use layers that automatically and adaptively learn spatial hierarchies of features, from simple edges to complex objects. This makes them the backbone of most modern image recognition systems, powering everything from photo tagging to medical image analysis. Might wonder, why are CNNs the go-to choice for image recognition? The answer lies in their unique architecture. CNNs are designed to automatically detect important features in images, such as edges, shapes, and textures without any manual intervention. This ability to learn directly from raw pixel data makes them incredibly powerful and efficient. As a result, CNNs outperform traditional methods in tasks like object detection, facial recognition, and even self-driving car vision systems. CNNs are inspired by the way our own brains process visual information. In the human visual cortex, different neurons respond to specific visual stimuli, such as lines or colors. Similarly, CNNs use layers of artificial neurons that specialize in detecting different features in an image. This biological inspiration allows CNNs to break down complex images into simpler components, making it easier for computers to understand what they're seeing. The core of every CNN are its layers. Each layer has a specific role in processing the image. The first layers typically detect simple features like edges or colors. As we move deeper into the network, the layers start recognizing more complex patterns, such as shapes or even entire objects. This hierarchical approach allows CNNs to build a detailed understanding of the image, step by step. Convolutional layer is the heart of a CNN. It works by sliding small filters over the input image, looking for specific patterns. Each filter is like a tiny window that scans the image, detecting features such as edges, corners, or textures. The result is a set of feature maps that highlight where certain patterns appear in the image. This process is what gives CNNs their name and their power. After convolutional layers, CNNs often use pooling layers to simplify the data. Pooling reduces the size of the feature maps while keeping the most important information. Think of it as summarizing a large image into a smaller, more manageable version. This not only speeds up processing but also helps the network focus on the most relevant features, making it more robust to variations in the input. Activation functions are crucial in CNNs. They introduce nonlinearity, allowing the network to learn complex patterns. The most common activation function in CNNs is the ReLU, or rectified linear unit. It simply turns negative values to zero, making the network faster and more efficient. Without activation functions, CNNs would struggle to model the rich variety of patterns found in real-world images. Towards the end of a CNN, we find fully connected layers. These layers take the high-level features extracted by previous layers and use them to make final predictions. In image recognition, this could mean identifying whether an image contains a cat, a dog, or a car. Fully connected layers act as the decision makers, combining all the information gathered to produce a meaningful output. CNNs learn through a process called training. During training, the network is shown thousands or even millions of labeled images. It adjusts its internal parameters to minimize errors in its predictions. This learning process is guided by an algorithm called backpropagation, which helps the network gradually improve its accuracy over time. Data is the fuel that powers CNNs. The more diverse and extensive the training data, the better the network can learn to recognize different objects and patterns. High-quality datasets help CNNs generalize well, meaning they can accurately identify new images they haven't seen before. This is why collecting and curating good data is so important in building effective image recognition systems. In building a CNN, it's important to separate the data into training and testing sets. The training set is used to teach the network, while the testing set evaluates how well it has learned. This ensures that the CNN isn't just memorizing images, but actually learning to recognize patterns that can be applied to new, unseen data. Overfitting is a common challenge in training CNNs. It happens when the network learns the training data too well, including its noise and quirks, but fails to perform well on new data. To prevent overfitting, techniques like data augmentation, dropout, and regularization are used. These help the network generalize better and make more accurate predictions on real-world images. Data augmentation is a powerful technique to improve CNN performance. By making small changes to the training images, such as rotating, flipping, or adjusting brightness, we can create more diverse data. This helps the network become more robust and less likely to overfit as it learns to recognize objects in different conditions. Dropout is another technique to combat overfitting. During training, dropout randomly turns off some neurons in the network. This forces the CNN to learn more robust features as it can't rely on any single neuron. Dropout is simple but highly effective and is widely used in modern CNN architectures. Regularization methods such as L2 regularization add a penalty for large weights in the network. This encourages the CNN to find simpler, more general solutions rather than memorizing the training data. Regularization is a key part of building models that perform well on new, unseen images. Over the years, several CNN architectures have become popular in the field. Examples include LaNet, AlexNet, VGG, GoogleNet, and RaiseNet. Each of these architectures introduced new ideas and improvements, pushing the boundaries of what CNNs can achieve in image recognition tasks. LaNet was one of the first successful CNN architectures developed in the 1990s for handwritten digit recognition. It laid the foundation for modern CNNs, introducing key concepts like convolutional and pooling layers. LaNet's success demonstrated the potential of deep learning for image recognition. AlexNet marked a major breakthrough in 2012 by winning the ImageNet competition with a significant margin. It used deeper networks, RAY-LU activation, and dropout, setting new standards for image recognition. AlexNet's success sparked a surge of interest in deep learning and CNNs. VGG networks are known for their simplicity and depth. By stacking many small convolutional filters, VGG achieved impressive results on image recognition benchmarks. Its straightforward design made it a favorite for researchers and practitioners alike. GoogleNet introduced the Inception module, which allows the network to process information at multiple scales simultaneously. This innovation made CNNs more efficient and powerful, enabling them to handle complex images with fewer parameters. RaiseNet, or residual networks, solved the problem of training very deep networks by introducing shortcut connections. These shortcuts help the network learn faster and achieve even higher accuracy. RaiseNet's design has influenced many modern CNN architectures. Transfer learning is a powerful technique where a pre-trained CNN is adapted to a new task. Instead of training from scratch, we use a model that has already learned useful features from a large dataset. This saves time and resources and often leads to better performance, especially when data is limited. Fine-tuning is a common approach in transfer learning. Here, we take a pre-trained CNN and adjust its weights slightly to fit a new dataset. This allows the network to retain its general knowledge while adapting to the specifics of the new task, resulting in faster and more accurate learning. CNNs are everywhere in our daily lives. They power facial recognition on smartphones, enable self-driving cars to see the road, and help social media platforms tag photos. Their ability to quickly and accurately interpret images has made them indispensable in many modern applications. In healthcare, CNNs are used to analyze medical images like X-rays and MRIs. They help doctors detect diseases, identify tumors, and even predict patient outcomes. By automating image analysis, CNNs are improving accuracy and saving valuable time in medical diagnostics. Self-driving cars rely heavily on CNNs to interpret visual data from cameras and sensors. CNNs help these vehicles recognize pedestrians, traffic signs, and other vehicles, enabling safe and autonomous navigation. This technology is paving the way for the future of transportation. CNNs are also used in security systems to monitor video feeds and detect suspicious activities. They can identify faces, track movements, and even recognize unusual behavior, making public spaces safer and more secure. On social media platforms, CNNs automatically tag friends in photos, filter inappropriate content, and organize images. Their ability to understand visual content has transformed how we interact with and share photos online. Despite their success, CNNs face several challenges. They require large amounts of labeled data, significant computational resources, and can be vulnerable to adversarial attacks. Researchers are actively working to address these issues and make CNNs even more robust and reliable. Adversarial attacks are a unique challenge for CNNs. By making tiny, almost invisible changes to an image, attackers can trick a CNN into making incorrect predictions. Understanding and defending against these attacks is a hot topic in AI research. Training and running CNNs can be computationally intensive. They often require powerful GPUs and large amounts of memory. As CNNs become deeper and more complex, optimizing their efficiency is an ongoing area of research and development. The future of CNNs is bright. Researchers are constantly developing new architectures, training methods, and applications. From real-time video analysis to advanced medical diagnostics, CNNs are set to play an even bigger role in the years ahead. While CNNs are best known for image recognition, they're also used in other fields. For example, they can analyze audio signals, process video frames, and even help in natural language processing. Their versatility makes them a valuable tool across many domains. CNNs are often combined with other types of neural networks, such as recurrent neural networks (RNNs), to tackle more complex tasks. For instance, in video analysis, CNNs extract features from each frame while RNNs track changes over time. This combination unlocks new possibilities for AI applications. As CNNs become more widespread, understanding how they make decisions is increasingly important. Researchers are developing tools to visualize and interpret the features learned by CNNs. This helps build trust and transparency in AI systems, especially in critical applications like healthcare. With advances in hardware, CNNs are now being deployed on edge devices like smartphones and cameras. This allows for real-time image recognition without needing to send data to the cloud, improving speed and privacy. Robots use CNNs to interpret their surroundings, recognize objects, and navigate environments. This capability is essential for tasks like warehouse automation, delivery robots, and even robotic surgery where accurate perception is critical. CNNs are used to analyze satellite images for applications like agriculture, environmental monitoring, and disaster response. They can detect changes in land use, identify crop types, and even spot signs of deforestation from space. CNNs are also making waves in the world of art. They can generate new images, enhance photos, and even create unique artistic styles. This blend of technology and creativity is opening up exciting new possibilities for artists and designers. Retailers use CNNs for tasks like product recognition, inventory management, and customer analytics. By analyzing images from cameras and sensors, CNNs help businesses optimize operations and improve the shopping experience. As with any powerful technology, the use of CNNs raises important ethical questions. Issues like privacy, bias, and accountability must be carefully considered to ensure that image recognition systems are used responsibly and fairly. Open-source frameworks like TensorFlow and PyTorch have made it easier than ever to build and experiment with CNNs. These tools provide powerful libraries and resources, enabling both beginners and experts to push the boundaries of image recognition. If you're interested in exploring CNNs yourself, there are plenty of resources available online. Tutorials, datasets, and open-source code can help you get started with building your own image recognition models. With a bit of curiosity and persistence, anyone can learn the basics of CNNs. To wrap up, convolutional neural networks have transformed the field of image recognition. Their ability to automatically learn and extract features from images has enabled countless applications from healthcare to entertainment. As research continues, CNNs will only become more capable and widespread, shaping the future of technology and our daily lives.